Okay, so start while Hurwitz Moduli equation and level structure. Okay, I'll start with something very classical done by Pierre in 69 with Mumford. So if 2G is largely equal than 3, then there is such a diagram of moduli spaces of coarse spaces and fine moduli spaces of curves of genus G. And this guy is very nice. It's proper, smooth, modular, and also everything is over Z. That's the sort of ideal situation. After that, actually, it was addition by Knudsen and Mumford. Also very important that one can also add here N, and get a similar picture for N-pointed curves. And this time, this guy is parameterized as nodal N-pointed curves CT and union of Ti over T. And this guy parameterizes smooth. Okay, and what are tools for this story? Just some tools. First, for properness or stable reduction, one needs some evaluative criterion, and it says that up to a finite extension of R prime of R, which I completely ignored. State theoretic issues, yeah, we have here quark spaces, but modular interpretation and smoothness holds only on the level of refinement to steps, of course. And stable reduction says that for any evaluation ring R with fraction field K and residue field.
Sorry, so can I ask a question?
Yeah, sure.
So the M that's not a script M is coarse.
Coarse is usual and script is fine. Yeah.
And the bar means the
Compactification.
So should there be a bar on the right instead of the left?
Yeah.
Thanks.
Oh, God. Yeah. Okay. Yeah, and for such a thing, you have that MGN bar is actually of R, restricted to K is MGN K. So if you, non-trivial thing here is that if you start from a curve over K, you can extend it and extend uniquely, and it was the question how to design these conditions in order to ensure this. So this is what underlies this. Stable reduction actually it has many phases. In my view, it's first of all a resolution result in sort of dimension 1.5. And it's relative resolution, and then as well this framework, it's very surprising, and it afterward was used by de Jong, DAX resolution and so on. It's a bit surprising that it wasn't discovered before by Zariski and his group. Of course, it was discovered completely from different direction. Yeah. Let's start. So, okay, and there is 1.5, which is sort of underestimated probably here. It is schematical density. And no new components, no new components. Yeah, you want compactification, you want to get something proper, but you don't want to add something, of course. And this means that actually you have a lifting result. That is, if you take M, let me just write M without Gen, M of K, which is embedded into M bar of K. And then you can from here take a map to M bar of small, restrict, because of this identification, then restrict, and this guy should be onto. So you can take any nodal here and smoothen it over general fiber. Yeah? So this indicates that it is schematic. And usually this is subsumed in other stuff, but I would view it as part of stable reduction, as part of compactification issue. And two, this guy is M bar M is a normal crossing pair. And well, you use some deformation theory and you study it over K of epsilon. And yeah, good. So these are standard tools. Now,
wait, sorry, what was this comment about dimension 1.5, you said?
About resolution.
Yeah.
Why it is in 1.5.
Yeah.
Okay, because you sort of work with surfaces, but you release one entire dimension, you allow extend. And if you look on how it behaves with respect to resolution of surfaces, it is easier. It is usually deduced from resolution of surfaces, but it's sort of cheap trick. I mean, you go in easier direction. And when you consider the complexity, it's almost the same, but when you resolve surfaces, you also have self-intersection things, and you have a bit of more complications. Okay, but they are morally close. It's sort of philosophical remark, it's not, okay. Okay, good. Now, so this is about dimension 1. Now, in dimension 2, moduli spaces behave much worse. If we consider general moduli space of surfaces, it satisfies Murphy law, no smoothness, and whatever. And if you restrict to, I know, okay, free surfaces, you have nice spaces, but you have supersingular components. You already don't have it smooth over Z. You may have components. And but one can ask again about 1.5. Moduli space in dimension 1.5. What I want to let's erase this. And this is Hurwitz stuff. Again, it's completely informal. This time, completely informal. So Hurwitz spaces. I'll denote just to state my notation. H corresponds to D, G, and G prime and prime lambda. And this time we want to parameterize C, the joint union of TIs, mapped by a morphism of HT. C prime and the joint union again, of course, of T. And prime, both are mapped to T. And we want a degree of this HT. to be equal to D. G and this genus here, G prime genus here. And we want preimage of marked points to be marked points. And we want this guy to contain a ramification of HT to control ramification by marked points, which are sum of lambda I. Okay, so these are multiplicities. And we want to mark them. Now, there are different ways to formulate it. Of course, with such amount of data, we can consider all sorts of changes. Sometimes people do not order the markings. Sometimes, so there are different situations. I view.
What kind of curves can be singular?
Okay, in this case, smooth proper. But we'll immediately, yeah, so.
Sorry, here the points are ordered also. Here the points are ordered.
Yes, because of this
Yes.
Gn prime. That's precisely what was my remark, but in principle you can not order them, but it's always better to solve situation when you impose more level structure because it's easy to forget. So if you are able to impose more. It does not, yeah.
But the DI are these problems. The bounds are these.
Yes, and ordered and ordered.
Yes.
Yeah.
But
Yeah. If they intersect, they cannot be ordered.
yes.
So.
Family good. As a family, they're good.
Yeah, okay, yeah. Well, and this time again, so maybe I should also say with remark, classical situation here is when G prime is 0 and lambda I are 2, just simple double points, and also one wants them in each fiber to have just at most one system.
Sorry, where are the lambda?
You did not speak about lambda.
Where is lambda?
Lambda is ramification, so this is ramification pattern. And in such case, one used notation HD GN, just number of double points, genus and D, and
So it's all stack.
yeah. And there is a similar picture, H core space, embeds into compactification, embeds into this. But it works well only when let's say when ramification everything is tame. Only let's say in tame situation, which means that we walk over Z with all primes up to D inverted. So we cannot have inseparable components. We cannot have wild ramification points in our pattern. Okay. So in such a situation, this was constructed by Harris-Mumford, at least for classical situation. And this was constructed by Abramovich-Oort-Vistoli. It involved more subtleties because of some static curves, and a modular interpretation of such a thing was a bit more subtle.
Enough to have the lambda I invertible. Oh,
Because even in our example, which we'll discuss with modular curves, you can realize it as empty pattern. And modular P, you feel that you're down.
Yes.
So inseparable components can show up even if you think they are not forced by it. Okay, good. So now what I wanted to say here.
Where's the problem is which fits the problem?
Yeah. We'll immediately, remark about properties. And this time, this thing is given by simultaneous stable reduction. You want to find a model where you have a finite morphism and both are nodal and you cannot blow down components. Okay? So this is not precisely how, okay, yeah. So simultaneous thing. Now, the problem with simultaneous thing.
Now do we allow the curves to be nodal? But
Yes.
the EI cannot be nodes, I expect.
I'll say it here now. We wanted simultaneous stable reduction or what is called admissible covers, which means that they are log attached. So if you have nodes, then over nodes you ramify the same over. So you allow ramification of order n over both nodes. This is called admissible covers. This was the discovery of Harris Mumford. What to put here, but then it was a bit of stack theoretic issues with this structure, so modular function was subtle. It's not important for us. I'll not go to details, but that was the reason why I took two steps about it. Now, but what is important for us is that this completely breaks down in characteristic P. The simultaneous stable reduction is easy. It follows from usual stable reduction relatively easily. Because once you have stable reduction, you have cofinal family of stable reductions. It's easy to describe. And when you can prove simultaneous. But you definitely, in characteristic P, can have inseparable components. Which, as we discussed, can just show up out of nowhere and they definitely lose information. So I mean, you can think that you have something proper, but you don't get a good functor because you lose information, and if you just describe it in this way, you get extra components. You have to impose some conditions which will cut out the components which are not needed. Okay, so one works, 1.5 doesn't. And of course, there is no hope for anything. So we first of all should understand how to restrict information. Good. Okay, so now maybe I'll tell 2 words about what I'll not discuss. So my personal story here started with attempt to understand how really what is the information hidden in covers of degree P in Berkowitz setting. Just stable reduction, but with microscope. In a sense, analytic spaces are best possible microscope operations. And trying to understand how inseparable components can show up and what is the general structure and what are invariants which control it. And when I came to a functor which compactifies this in degree P, I tried in some talk to give Berkowitz story, and I did not get anywhere, so just talk ended before me. Yeah, so it's better not to start. So I had to design another approach, and this is what I try to say now. So the idea of Abramovich-Oort. So, and yeah, just relatively recently, it's very funny because I'm working with Danny for years, but about this paper I just Occasionally, my student found it. Paper by Abramovich-Oort in 2000, I think. And we said, okay, let's try to study this question in simplest wild case. Simplest wild case is, I'll denote it H, and it is H24. So 2 is the degree, and 4 is the number of points. And genus is okay. Maybe I should say genus is 1, 0. 1, 4, and 0.
And we want unequal characteristic or characteristic equal?
We want to start with characteristic 0, and I'll immediately explain the idea and just take schematic closure. So, like what happens here, you saw that if we use schematic closure, sometimes we describe something simpler and after we try to refine. We want first of all to describe schematic closure without moduli functor, and then think what can be moduli functor. So we just want to parameterize covers elliptic to P1, degree 2, in over Q we know very well what it is. And we say that idea by Pandariphande we said that actually if you take H over Q, when we'll take its schematic closure in the moduli space of maps. Moduli space of certain maps. Morally, we want to realize a map from a curve to a curve as a stable map from one curve to another curve. So this is the idea. I will not write down this formalization, but what is important, this space using the MGNs was defined over Z. So it existed over Z, and with stabilization condition, we suspected that it should somehow help them to get something reasonable. Now I'll just write down what we got. It will be first series of pictures. So results. And the logic is
Sorry, so this is like the space of stable maps to a stack. Is that what you have in mind here? Or?
Yeah. Yes. Stable. We take. We say that if you want to study G going to G prime, let's say and prime, you take CG prime and prime over Gn in universal curve. And you take maps of curves of genus G to the universal curve. So formally we denote it in this way. So map from Gen to universal. But again, it's not important. So in characteristic over Q, the situation is very simple. We have lambda curve, which is this H. We have a map to J curve. J is given by U square lambda minus 1 square. Infinity 0, 1, infinity. When lambda collides with one of these three, will have something problematic. And the covers, now I want to describe how cover look like. So cover here looks like EJ mapping to P1 and ramified at 4 points, 0, 1, lambda infinity. And somewhere here, we'll get a picture which looks like this. And so lambda collided with 1, so we'll have 1 lambda and 0 infinity in this case. So because of collision of lambda and 1, we have to blow up to separate them, and then our curve cover looks like this. Okay, good. And now let's consider the.
So, other picture hanged up. What happens to each of one of the components?
It's ramified at 2 points, so it's ramified at 2 points.
Oh, yes, lambda and
yes.
this, yes.
Yeah. Okay, and now let's consider what happens over F2. So we defined our H as the closure, just some schematic closure. In our schematic closure, what we should remember, these 4 points must stay separate. So this is the main issue. We must stay separated in schematic closure. So let me describe first for maybe ordinary case. So in ordinary case, we have elliptic curve with invariant J mapping to P1, but this time we have just 2. So this is ordinary. We have just 2 ramification. We always can put them 0 infinity. Doesn't matter, but of course we have here collisions of. So if you think that we have a picture which goes from characteristic 0 to characteristic 2, our ramification collided twice, and this MGN, the N addition, blows up to separate. So it blows up, and then once it blows up here, you get really a separation of 4 points. And infinity, so the curve which you'll get over the curve from ordinary locus in this schematic closure looks like what is written here. The map between this guy and this guy is Frobenius. So it's inseparable. Inseparable map.
So if a new component and
Yes.
the 2D.
Yes, I took a wild ramification point, I blow it up, and I get a whole line of wild ramification points, but it's separated the ramification which came from characteristics.
What happens about to separated lambda and infinity?
Nothing special. There is no geometry here because these are just 3 points for Venus, so no geometry. There is a question which you asked when we talked that actually wild ramification points will have moduli.
Yes.
So you can describe J using this moduli. About this I thought after, so the answer is that these are simplest wild ramification points. In characteristic 2 we have just one parameter. It looks like y squared plus y equals ct, and this is a parameter, and you have 2 parameters.
But we have to dilate
and you have only one dilation, so you take J and J, factor diagonally, and this gives you.
Yeah. Yes.
Yeah. Okay, and now maybe I'll give the answer how this thing looks like. So H over 2 looks like P1 lambda, and 3 P1j's. At each of these points, j is equal 0. These are supersingular things. And the whole lambda, as we'll immediately see, is also this is supersingular locus. And these three guys are ordinary locus. Ordinary. But there are three of them. Why three? Because there is a canonical subgroup, the guy which sits together with 0. The degeneration from characteristic 0 can take any of another ramification point together with 0. And this choice actually defines you a choice of these three j's. By the way, from this guy, there are two maps. There is map to P1 lambda, map to P1j, map to P1 lambda contracts actually on P1, and maps on P1j identifies j's and contracts lambda. Okay, as a matter of computation, this is really a matter of computation. In the, let's say, deep supersingular case, when we are somewhere here, the picture looks as follows. First of all, we have E0 supersingular and characteristic 0, there is only one. And it has J invariant 0. In characteristic 2, there is just one supersingular curve. E0, it ramifies of infinity, but strongly ramifies this time all 4 points. Sit here, so we have to blow it up. And if we are deep inside, there is no priority between either of 4 points. They are all distant. So we have to separate simultaneously. So what you get here will be 0, 1, lambda infinity. And as a matter of computation, this point is always root of lambda, but there is no good reason for it. A simple reason. Good reason, of course, but no simple reason. So we just compute it. And you can argue by some symmetry, but in the middle situation is sort of transit from one situation to another. It must contain both components, and they look like E0. And when we blow up and only separate 2 points, separate pairs, pairs which are determined by one of 3 choices, then we have to blow up again, and only after that we separate it. Say 0, 1 and lambda 0, 1 will be in this case, there is no modular inside the question. Here, the modulus is J. J determines the geometry, and here the modulus is lambda. So this is precisely the illustration with some geometric information. If we just take reduction and no other information, we miss it. So we must, in this case, we included by geometry of ramification points. And we have a non-trivial condition which should drop the dimension from 2 to 1 by fixing this point. Otherwise, we would get something two-dimensional. So if we choose this point wrongly, we won't be able to lift. Okay? Good. And now, modular compactification. So now let's, in fact, I think the work of Abramovich-Oort finished here. So we computed one example. We did realize that this guy is the modular curve x of 2. It's just written there. I missed it first time when I read. But and what you get here is the Katz-Mazur compactification, which has 3 ordinary curves blown up at the intersection. So this component is tend on blowing up this thing. And in particular, it sits over Z with multiplicity 3. If you have three components, you blow up something and get sits with multiplicity 3. Okay. Now, modular computation. Of HT, D and D prime. So let's denote it. For modular computation, let's denote it. Okay, so main idea.
What kind of trainers and so on?
What kind of
Trainers of the group.
I wrote D. This is G, this is G prime, this is D, and we'll walk over D of 1 over 2 minus 1 factorial. So I do allow the generation of degree P, but as mild expression. And the idea is the following: just control ramification of HT, H infinite.
So H is the map.
Yes, H is the map from C to C prime. Yeah. So I would like somehow to write as nice as possible algebraic formula for this H and try to keep all information of ramification inside here. So I claim that if I restrict it stupidly, I just get Frobenius and I lose everything. But I'll be able to rescale it in a smart way and when the information is kept after reduction. That's the idea in one word. Honestly, it was, as I said, it was found in a different way. From Berkovich study, I knew what information should be, but this is probably the shortest way how one should have to write. So for simplicity, let me just consider absolute situations. So let's take K, just simplicity. And also let's take just smooth things. It will not be important soon. So we have this sequence omega C prime. I'll denote this guy tau H, omega C, and when you have here O of R of H, this is the sum of delta I pi, but delta I were completely not lambda I, were some other numbers. Yeah, so delta I were just not necessarily, were different of OTI over OP as prime. Always the same order of vanishing of D TPI over D TPI prime. Order of vanishing of informations. So we just take a sort of generator here, and
So that's the number which appear when computing the genes.
Of course. So Riemann Hurwitz says that twice g minus 2 equal to d times twice g prime minus 2 plus sum of that I. Okay.
And you assume if that it's separable map.
Here, yes. Here, yes. And now I want to do it in families. And in families, this guy can vanish. So I want to rescale by its order of vanishing on component. That's the idea. So when in families I have inseparable component, this guy will vanish. So I'll need to rescale it by order of 0 and then get an information. So what is the best way to do it? I'll describe it how. So instead of this thing, one should just consider tau h as a section of omega h, which is the Lorentzian sheaf. You take omega c and tensor with pullback of omega c prime. And when this is just a single sheaf and the Lorentzian sheaf, it goes well in any family. And in an inseparable component just will get 0, but we can just take such a thing and rescale it by order of vanishing on each component. So just now, rescale by order of vanishing. On CI. For example, just for illustration, I have picture.
You rescale between the land bundle or you want to change?
Okay, imagine. So let's assume that I have now DVR. I have a generic point and closed point. I have something smooth. But here I have few components CI. And on some components, my thing can vanish with some order of vanishing, order of tau h on CI. And then I'll want to take, instead of this thing, I'll want to view it as a section or a scale section of omega h twist minus a. And when I get something which does not vanish on any component, this time it will give me only a meromorphic differential form on any component because I twisted. So at nodes, I can get poles or zeros. This will be meromorphic guy. They are compatible due to the order of twisting, and its order of vanishing, or its divisor, after such thing will be precisely the ramification which goes from generic. So this is the guy which I really can see here, and it has this thing. A meromorphic differential form or relative differential form. Okay. And if in addition to this L, I'll take this L and divisor of T, divisor of tau, let's call it, I know, the prime. Then actually I can just view my tau as a witness that O is by tau is isomorphic to omega h twist minus h. So if I twist both by the divisor, by horizontal and by order of vanishing on vertical components, I just get no way vanishing it. So it's another formula to write this. And then finally, I'll just indicate because I don't want to dwell on this topic. I'll just very briefly outline the idea. So finally, final realization. It's done by my student Hippold, and it's a bit in progress. So what I say is in progress. So some things are written down, some things are just saying. One first of all switch to the category of log schemes. And we think about our functor as functor in category of log schemes, and then this H bar of T consists of three things. It's a map CT to C prime T, which is finite, degree P, and logical if not of degree P. It can have inseparable components, but everywhere at the nodes, otherwise it should be just logical. These guys are log smooths. Over here. But extra datum, there are two pieces of extra datum. There is LT, analog of vanishing order of what I want. Consider it's in families. It's the best, at least best possible form is my know is to view it as monodic of T over T. And when finally there is tau, which just witnesses that O is isomorphic to omega H. Twist this F. And in practical terms, it actually means that you, on each component of CT, you give meromorphic differential form, and poles and zeros on different components are matching accordingly to the difference which is measured by order of magnitude. The last thing, this guy should satisfy certain exactness condition. Morally, it's something like DHT after scale. I don't have, okay, I didn't plan to talk about this, but there is some non-trivial condition which actually responsible for cutting down our space to only liftable ones. So there is non-trivial condition which is needed to cut down. So we guess what is the datum we have on reduction for free. We start from something here, and we have a simple section on generic fiber, and I explain you how to reduce it to closed fiber without losing datum, and we get functor which is too large. So there is non-trivial condition we should impose. And this game seems to be more and more complicated when we study more complicated spaces. So it's not enough just to take stable reduction. You must guess condition which take out all parasitic components. Okay. Good. And now let's proceed to. Maybe just last remark about this. So we define something complicated. So there must be some. Okay, maybe I'll keep it. There must be some explanation, or at least some proof of concept, why we think that this space is reasonable. Maybe there are many compactifications. Yeah, so of course we have some gut feeling that we really restricted all possible datum, but yeah. And
you said you were using degree.
Yeah.
Would degree strictly smaller than p squared be good enough?
Currently, I think that if you, yes, but Yeah, I think so, but again, it's not yeah, not written. What part of this is written, so partially, is that this guy is log smooth over z is 1 over p minus 1 invertible and log p. So you add p to your log structure, and when you get something which is log smooth, but you must add this. And for simple reasons, in the examples like this, our closed fiber is nodal, so it can be only smooth over something with log structure. And in fact, as I explained, this guy, it behaves like 2 to 1 fillet. It has multiplicity 3 over 2, but for log smoothness it's enough. If I am prime to P, this is still log smooth. Okay. Good. And well, now let's discuss the next topic. Last topic. It's about while level. So this is about what I have to say about level while spaces. Maybe just two remarks. One can ask, what about d equal p to the r? General degree. Is it log smooth? Whatever. I can for sure say that instead of only tau, you must look for higher ramification filtration. And instead of different, you'll have all Erbrand function as discrete invariant. So it certainly should be more complicated. My hope was that with this more complicated structure, it will be log smooth, but now I think I have evidence that no, because of the second story. And second, this H24, which we discussed, it's blowing up at supersingular point of X2, let's say Katz-Mazur. We have different versions what X2 should be, but if we take Drinfeld level structure, it was done by Katz-Mazur, and we get a natural moduli space which is a blow up of this. Okay. So what about x of p to the n? And that's what I want to discuss now, using the same idea and using the fact that actually we saw that there is a good relation between Hurwitz and so this. In one case, we had a good relation.
Yes, but
for P, of course, you can think about this as if you establish this, you can think about this as Hurwitz space of degree P to n, 1, P to n, 1, 1, and empty ramification. Just let's classify all étale covers from elliptic to elliptic. Yeah, but this time when they become bad or inseparable components in degree P, let's apply the same machinery. This will contain, because of numbering of points, you'll have many copies of such a guy. But I suspect that you should get also something like that. But it's much more complicated. You must study this case. So it seems more complicated approach. And another approach is what I will describe now. Okay, so last point, wild level structures on elliptic curves. Although I do have hopes about a billion varieties after that, but good thing about elliptic is that many things are known here, and you can try to cross-check yourself with computations. And it went more complicated than I expected, so I would be glad, first of all, to double-check myself with all. No, even in Kathmandu, they do a lot of numerology, and I guess it's an indication that they wanted to double-check themselves from all directions, but there are no contradictions. So, okay. Now, main idea. Define schematic closure, just like what we saw with Abramovich-Oort. Start with more modest thing, define schematic closure of x e to the q. Of course, you can take here any number, not necessarily p to the n, but the prime to p thing will separate, and there is no real interaction. And moreover, you have just a product of this and that, and so. In final formulation, of course, you should do generally, but this is the main thing to think about. And let's define it, schema define of this in something. I immediately say, wow, so what?
It's Pn itself, you view it as elliptic curve and a map of C mod Pn squared.
Yes. So just fixing. I'll prefer just to norm number torsion points and just fix. Yeah.
So it's not the base, for instance, of the torsion point. You want
No, I want
the full C mod.
Yeah, the full. And then describe it. And guess we find. Yes. We find.
You did not say.
I mean. So and then try to guess the founder, and guessing the founder actually means that you have some first approximation, but then you have some parasitic things, and you impose condition, maybe another condition, and at some stage you should prove that you are done. But yeah, I have hopes what is enough, but I cannot say that it's. I'm confident. Yeah. So again, it will be mainly story about 1.5. Yeah. Now take gamma equals v mod p n z square. Gamma or gamma n, if n is clear, I'll just write gamma. And set, and let's take x into the n, closure of x, p, and q in just M1 gamma, maybe I'll say here first of all p to the n, but I identify this with gamma. The number, so I just fix one number in gamma. Of course, 0 will go to 0 gamma, and just anything. So this thing sits in Q, so I just close it. So this defines me. So now I do have something. It's not modular. Until I solve this, it's not modular, but it's some scheme. So it's reasonable to try to define related to Kathmandu. Try to guess the modular. Okay. So just as an example. First example. Unfortunately, I erased all these pictures, but in this situation, So it was naturally for, I know how I imagine maps, but here it's something very, very different. Let's take x of 2, which is h2 for bar, just by our definition. Yeah, by and then let's try to describe ex for x sitting in x2 2, maybe bar, and there might be three possibilities for good reduction. There is also bad reduction, but let me just ignore it. It's equal. So there is such a situation when I have V0. My 4 points from a leaf to characteristic 0 meet all together. I have to blow up. I get another component which is rational component. And when all my points separate. There is an ordinary situation which looks like this. And there is a case when I blow up and when they separate only two pairs, then I have to blow up. And I can even say this will be a J invariant, let's say equal to value of 4. This will be a J invariant equal 1. This will be this. And the generations go as follows. This guy shrinks here. This guy shrinks here. This is the same picture which we had before. And in general, well, I'm out of time. In general, the picture looks as follows in ordinary situation. X e to the n of fp bar looks like something like this. On the bottom level, we have an extension of additive group by gamma, and gamma embeds into the group below, which is extension of J by gamma modular gamma. Let's say if this is gamma 0, what sits in the component, in the connected component of 0. When the components, the J components are parameterized by gamma. Okay, and ordinary case is sort of always the same because all the structure is the same as mu p to J. So all lengths here, if you walk over log of p, then all lengths with respect to log p will be predicted. Everything will be predicted. And I have to hurry up, because I'm over time, but yeah. There is one can add logarithmic picture, and this is complete. And in case
you tell the picture of what things you get by.
I just say that description of k points is simple.
Yes, but you have many more things than what you want.
In this,
you did not express the fact that gamma is a group. Okay. So yeah, let's say sorry. We have E is a genus 1 curve, genus 1. Gamma embeds into gamma x on E So where the restriction of gamma to gamma is shifts. This already this condition restricts you very much to what's going on, and you get here this extension of GA by cosets of gamma. And moreover, all splittings happen by additive group and cosets. Yeah. So this already restricts very much what can happen. On each level, you have ramification by P or P squared, but no more than that. And then once you try to describe the general picture, maybe I'll just show the answer what we get for geometric points. So geometric points. So for n equal 1, you get ordinary for p plus 1, ordinary, and 1 supersingular. Supersingular looks like p squared. It looks like P supersingular when P1. When you have P square things, and the parameter here will be lambda, which is cross ratio of 0, infinity, and 2 generators. This group has 2 generators and cross ratio of 2 generators. And ordinary corresponds to the choice of canonical subgroup out of you have people plus 1 choices. Yeah, so of course what we have here was a particular case. And of course this should be just blow up of Katz-Mazur at each supersingular point. This guy will show up with multiplicity p plus 1. So, and if you take n equal 2, then this will look like this. So this time you have maybe just any. You have Pn minus 1 times P plus 1 ordinary components. They are organized in such a shape. And maybe I'll just, I'm really hard over time. So I'll just say what I think should be really the information which is enough, but I apologize, but was over pretty for time. I think that let's say working conception. Xp of n is n1 gamma with action of gamma. So this is precisely what I said with gamma x on. This is enough to describe k points. At least, okay, up to some simple combinatorial exceptions, you can say that if the graph is very strange, you should remove it. But the restrictions I mentioned already. But in addition, you have a differential form, which is scaled reduction. So in characteristic 0, we have invariant form. So you should, like we described earlier, you should take this form and restrict it with scalings. So
we have a form. You can choose one, but it's not part of the data.
It should be okay. You have somehow it's unique up to scalar onto omega e twisted by some degree, by some level functions of degrees on each level. So it's 0 on top level and then 1, 2, and so on. And you should just fix one such thing. So in the picture of elliptic curve, it will correspond to invariant form on elliptic curve, something like dx on one level, something like, I know x1, dx2 on the other level, and so on. But the choice of dx on with respect to given coordinates, the choice of dx on each thing will is responsible for the additive structure on different components. Okay. And a surprise for me was that although geometric points are okay, if you study deformations, without this condition, deformation, you have parasitic deformation. This is not similar to other situations. Morally, the action of gamma, which is purely additive here, can go to multiplicative action, nilpotent multiplicative action when you deform. The automorphism of GA is J cross G, not automorphism. Automorphism of advantage, which fix infinity. It's J extension G. Our group must sit here. For geometric point, there is no problem because G does not contribute. When I start to deform, I get nilpotence in G. So I can deform the action in bad direction. If I start to deform it in this direction, I will not be able to lift in characteristic 0 after high deformations. The only natural way to kill this is to request this to be compatible with this differential form. Okay, I did not find. But also somehow also from Hurwitz space and so on, this differential form seems to be a natural ingredient in all the picture. I mean, it's for example, it's used to find all these logarithms of the lenses. And
so are you starting in characteristic 0 with some dimension 2 moduli space, elliptic curve plus a differential form? And to get also something of dimension 2 as moduli space?
No. It should be just invariant differential form.
No, but that's the data. That's one parameter.
It's not parameter. It's
the moduli space just for elliptic curve is one differential form. That's V2 and V3.
Yeah. You say that there is well, okay, but okay. Yeah, you can just rescale it. You mean you can multiply it by a constant. But this should not. Yeah, just make a choice. I mean, again, I did not think how to formalize it best, but you can use either. It won't change the. So you should just identify up to rescaling the form. Yeah, and the last piece is that you must take something like piezo. This piece also only needed when n is larger than 1, but even for geometric points, you'll get too large space without requesting that there exists piezogeny, which morally
dividing by gamma.
Yes, you take your E. Let's say you have gamma 1 and inside gamma n map onto gamma n minus 1. So you take E divided by gamma 1, and you want this to be isomorphic to the following thing. You take E and stabilize it only by gamma n minus 1. So out of all marked points, keep only gamma n minus 1. The curve destabilized components, it retracts onto subgraph. And this subgraph should be isomorphic to, There are some pictures for level 2 which are already quite interesting, but I think I will stop here. Yeah, okay. I apologize for being much over time.
Was it fun if any also a compatibility with the differential form?
Say it again?
So you want some maps between something corresponding to the multiplication by P map.
Okay.
But the differential form.
P is just condition. This isomorphism, if it exists, it should be it's not. It's just condition against us. But no, I can. Let's say so. In your work on generalized elliptic curves, yeah, you have a group law which is just Picard. Now here you can you have a group law on the bottom level, but I don't know how to describe it like Picard. The only way which I can suggest is that these are those automorphisms of the curve which respect the differential form. This is the real way why it shows up, and for families it starts to be important, because when I just in geometric case I can say, okay, by hands I take GAs, but when I start to take important thickenings, if I have an elliptic curve with additive model, then it's a more subtle thing how to describe the group law there. I don't have a good formula. And my description is that these are just automorphisms which respect this differential form. So it serves to reduce the automorphisms to the needed level. And if I have more automorphisms than needed, when in deformation, I get wrong directions for deformation. This is the real meaning. So I spent some time trying to find any analog of Picard or Picard with connection, whatever, any reasonable formula how to do such addition. I